Hello, everyone. Today, we'll be talking about some chemistry. So, what we're mainly talking about today is the periodic table of elements, its history, how it became a thing, and different groups of elements on the periodic table, and why those elements are placed in their specific spots on the periodic table, right? For example, why is iron where it is? Why is sodium where it is, right? We'll be going through all that today. So without further ado, let's start with some history of how the periodic table was created. So a Russian scientist by the name of Dmitry Mendeleev created the table in 1896. Right, he drafted up in 1896. The original periodic table elements. If you look at it, you'll be like, "Why does that look so weird?" Right? It would kind of look to you like it's incomplete, and that's because it is, and it's because a lot of different elements were actually discovered a lot later after the periodic table was first suggested, and a lot more organization of the elements took place for the periodic table. The periodic table of elements actually underwent a lot of changes from its first appearance. But the appearance of the periodic table of elements was actually quite a revolutionary event in chemistry, as it allowed scientists to be able to organize and categorize different elements they have found, and also predict um, the elements that they should be looking for, all the way down to their color, their chemical properties, and to the number of protons and electrons they have, just basically based on where the atom, like the element's supposed to be on the table and its neighbors, right? So this is just some objectives that that you're supposed to learn from this course, and we're gonna move on. Okay, so many of the same periods do have similar properties. So basically, what this is basically meaning that there are 7 periods on the periodic table, periods. You know, you get the idea. So there are 7 of them, and they're basically 7 different groups, right? And basically 7 different groups of elements. And as this slideshow has cleverly put it, horizontal rows. So basically, the periodic table of elements, um, each row, each like row down is a period. Members of the same period does not have similar properties means that a lot of times when you have like a row, the top of the row, the element at the top, could be vastly different from the elements down below. Take the first row, first period, for example. You got hydrogen on the top. Hydrogen is incredibly different to a lot of the other elements on there. For example, as we'll talk about later, a lot of those elements are incredibly reactive, but hydrogen is not, right? Now, members of the same period have the same number of electron energy levels, but they differ in how they're filled. So, electron energy levels are basically this thing where you have the nucleus of the atom, and you have like shells and or energy levels where electrons can be floating around near these nucleus, right? And so the amount of shells that all of these atoms in the same period, they have the same amount of shells, but the amount of like how much electrons actually there in the shells is incredibly different. For example, let's say a element whose atom has 3 shells, he can have all of them full. But then in the exact same period, he can have elements with 3 energy shells, but the most outer one is not full, right? And that actually buys into the properties being different, and it is because like if your energy levels of the electrons are not fully full, then you're a lot more reactive than if you are, right? Basically meaning you're more likely to undergo chemical reaction with another element. Actually, let me get my camera here. Okay, so some periods on the table are much larger than the others, right? Yeah, so basically, a periodic table shaped like this is not a perfect rectangle. There is some dents in there, and there's some bumps in there, and then there's a big section down below, right? So if you take whereas there's a bump and then there's a big section down below. That's a lot longer than when in the middle there's like a little dent and then there's like no section. You get the idea, okay? Right? So scientists basically classify materials with three basically main kind of like general categories. And basically those categories are metals, non-metals, or semi-metals. So I think most of you understand what are metals and what are non-metals, but what are semi-metals? So let's look at semi-metals first, and it is down here. Semi-metals or metalloids are located between metals and non-metals on the what just happened on the periodic table. They fall along a zigzag line that divides metals and non-metals. So the zigzag line, right here, that's metalloids. So basically, all semi-metals on the periodic table are solid at normal room temperature. And here's some examples, right? You have silicon, arsenic, and germanium. Look, germanium is discovered by Germans. People. Okay, and also, if you don't recognize a lot of these elements on here, arsenic is the most famous poison of all time, and it's a poison that doesn't leave any trace after killing you. And forensic scientists are still struggling on how to figure out how they actually test for arsenic poisoning. Silicon. If you go watch a movie or some other things, right, if you see a fake limb, it's most likely made of silicon. Boron and germanium are interesting. Okay, now non-metals, they're usually on the right side of the periodic table, so like right here. And with one little exception right here. And if you guys don't know, this is hydrogen. Hydrogen's like a little loner over here. They're generally gases or solids at normal room temperature, which means that they don't like to be in the middle. They like to be in the extreme, right? Either I'm solid or I'm a gas. I don't like to be in the middle, right? I'm not the middleman. Most solid non-metals are dull and brittle. For example, trying to think of an example on the top of my head here. Maybe like carbon, right? And then some gas. You have like all the gases here, and then you have gases here like hydrogen, and then over here you have like argon and stuff. Metals are mainly on the left side of the periodic table, and as it's decently obvious, metals are the biggest family in the periodic table. We're a big family. Okay, enough of that. So metals tend to be a solid at room temperature. That was weird. 75 degrees Fahrenheit. 75 degrees Fahrenheit is around 26, 28-ish degrees Celsius. Not certain. Most of them appear gray and metallic-ish, and some common features of metal are conductivity, which is the ability to conduct electric currents through them, malleability, and ductility. So basically, these two very, very hard to pronounce words basically mean the ability to, number one, be flattened into a really, really thin piece, or the ability to be stretched really thin, right? That's why if we have like, let's say, iron fences, but we don't have brick fences. We don't have like the same pattern for brick fences, right? Like those iron fences, they go like they're like those little diamond shapes, right? Can you form that with bricks? Yes. And then they'll fall over by touching it. It'll be like one of those little card houses, because a metal can be stretched, right? Iron, after you heat them, they can be stretched and molded into different shapes. And luster, which is them having a little like glow. There's one exception to metals, and it's not a liquid state at room temperature, and that is mercury. Mercury is a metal, and if you don't know, it's actually quite toxic, and it is commonly used in this thing called thermometers. That, number one, can tell us, do we need a coat or do we need a t-shirt outside? And two, can tell us, should we go to the hospital and try to test for coronavirus or just chill at your house, right? They're using thermometers. So elemental groups. Now we're getting more like, deep into it, more separate. We're separating them based on their quality. So first group, we have alkaline metals. So If you hear the name alkaline metals, it might remind you of a bottled water company. But don't let the nice little name fool you. The members of the alkaline metals family are incredibly reactive. So, group one alkaline metals, they're basically the entire first period or the entire first row on periodic table of elements, except for hydrogen. I know at this point, hydrogen sounds like one of those people that should be in the antisocial social club. I understand. Hydrogen. I empathize with you. You don't fit in. We're different. Okay, now anyway, back to alkaline metals. So alkaline metals are incredibly reactive because they have one of two scenarios, right? On one side, they can have basically on their most outer shell of their electron shells, they have one single electron, so they really want to get rid of it, or they have 7 electrons and they really want another one to make it 8, and 8 is the magic number. 8 is like, perfect. Now this means that elements from this group is constantly to either force feed another element or another atom as extra electron, or bully and steal, I don't know if I should put it that way, from another atom to basically form its full valence shell and get a full shell, right? This means that they're really quite reactive, and especially with water, right? If you have tried to put sodium or potassium in water, what's going to happen is it's going to fizz, there's going to be a lot of steam, and it's going to be a late explosion. There's one element near the bottom of the alkaline metals group. I can't really exactly remember his name, and that is because that element is so useless because it's so dangerous that it's basically completely useless. I'm just repeating myself here. And it's basically classified material that, for example, in the US, only the Army has access to. And if you want to get testing with it, you have to ask the Army. And that element, like this much of it, you throw in the ocean, it creates a humongous explosion that, if you stand close enough, will trick you into thinking it's a nuclear weapon, but it's actually a lot smaller. Yeah. But if you get a big enough quantity, I guess, technically you can use it to start a tsunami, huge explosion in the water. Okay, we're getting carried away here, but back to the qualities of alkaline metals. They usually have very low melting points and oxidize. So basically, again, low melting points, they have low melting points. Oxidize kind of plays into their high reactivity, right? Oxygen, they're reacting with oxygen. Oxygen is also quite reactive. It's not as reactive as the alkaline metals, but it's also quite reactive. So, after the reactive form, they usually form a new substance, and, it becomes dull when exposed to air, right? So they're extremely reactive, right? And they're rarely found in element form. So basically this means that if you go to nature, right? So for example, you walk into your backyard, there's a chance you can find pure metal, right? There's a chance you can find pure steel, for example. There's even a chance you can find pure coal if you dig, or pure gold maybe. But there's no chance that you're actually gonna find pure sodium. And that is because those elements are super reactive. They usually just end up either reacting or getting absorbed by different other stuff, right? And that's why it's super hard to find pure forms of these elements in water, right? Since they have only one electron in the outer energy shell, they can technically also have almost full and have one missing. That's a rare case scenario, and they're also very likely to give that electron away, right? So now we have the second group, which is alkaline earth metals. So alkaline earth metals, basically, technically, they're still quite reactive, but they're not as reactive as the alkaline metals. Oh wait, yeah, I just realized it. Look at this table of elements. Here are those short periods, and these are the long ones. There. Now, coming back to this. So in property form, they're usually a lot harder and denser than alkaline metals. So for example, if you're brave enough to take your little finger and go knock on it, you feel that group metals and other materials in this group are a lot more dense and a lot harder than in the alkaline metals. They're very reactive, but they're a lot less reactive, right? So let's say this is a very bad example, but let's say alkaline metals are nuclear weapons. Well, these guys are normal bombs. Both bad, both reactive, but these are a lot less reactive. And that's why you can see that a lot of these materials are actually a lot more, heard about by you. For example, calcium over here, right, which is part of your bone structure. So they have 2 electrons in the outer energy layer, and when they react, they tend to force feed those 2 electrons away to other elements, right? They are found in Earth crust, but not very, 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 very rare, again, elementally. So again, they're still too reactive to be found purely very often, right? For example, what's the chance you're going to walk into your backyard, start digging, and find a pure piece of calcium? Like 0, right? You can find calcium by taking a knife, cutting off your hand, dumping in a sulfuric acid to burn out all the flesh, and then somehow isolate the calcium from your bone. But we suggest you don't do that at home, right? Don't DIY find calcium. Dangerous. Now, this is a quick just periodic table of elements, and just so you guys can have a look. I don't know what this is here. Okay, elemental groups. There's another group of things called transition metals. So transition metals are basically, they're not that reactive any longer. A lot of these metals in here also are technically loners and outcasts, and they don't really fit in groups. So they're not reacting to be in here, and they're metals, and they are also a bit reactive, and they can't go in groups over here. You get it? So now so basically transition metals are the loner band. Okay? So they usually have good ability to conduct heat and electricity. They are usually very hard metals and have high melting points. And they have low to moderate radioactivity, right? And that's very important to note because metals in this era, they are radioactive. Which means if a prolonged exposure to them can technically mean they're carcinogenous. Just putting it out there. Don't sit next to transition metals for 5 hours a day. I won't. Most elements can only use electrons from their outermost orbit to bond with other elements. That's the reason why those previous ones are so reactive, and this one isn't really, because a lot of elements in here, they're a lot more stable. A lot of common ones in here. We have like iron in here. Oh yeah, guys, just by the way, forgive me. Steel isn't an element. I messed up. I previously said it is. Sorry. Okay. Well, cool. Yeah. We freely like metal is in here, right? Silver and gold. Yeah, basically everything that humans like to use. Yeah, you got copper here as well, nickel, tin. Those are the slightly more harmless ones. And from this list, you can technically see that the ones that they've never heard of usually are either radioactive or absolutely useless. And the ones that you have heard of are usually very common and very well used and very safe. So now the last elemental group not the last elemental group. Another elemental group we're going to talk about is halogens. So halogens are gases that have a certain amount of reaction activity, right? Some common ones in here are chlorine and fluorine and bromine, right? I and E, got that coming in. So you wonder why I say these guys are reactive. That is because pure chlorine is reactive. Pure fluorine is dangerously reactive. So if anybody hands you some pure fluorine and you just dump it on the ground, there's a chance the thing's just going to start catching fire randomly because there's a chemical reaction with a lot of heat. Pure fluorine can ignite a material that's previously thought to be unignitable. For example, concrete, asbestos, Chlorine and bromine are like slightly better, right? Chlorine you can be found in your pool. Why is it found in your pool? It's not found in the pool to kill you. It's found in the pool to kill the bacteria. Why can it kill the bacteria? Because it's reactive enough that it can go in with the bacteria and punch holes in the cell wall and kill it. Okay? So now, this is the last group we're technically going to talk about in the periodic table of elements, noble gases. So if you wonder why this is here, is because a lot of times when noble gases are subject to high heat, they start glowing. They don't melt or anything. They just glow like this. If you go see a lot of those signs out there that like open, that's like this, and they like, you know, stay, the sign stays open and says open. You get the idea? So a lot of those are basically their tubes with different types of noble gases running through them, and when the sign is open, okay, I gotta stop. Okay, when the sign is on, electric current is running through and heating up and energizing those noble gases, causing them to release gas. Some famous ones are like argon, for example, right? Neon, helium. Okay, by the way, interesting about helium is if you inhale some helium, your voice changes periodically to this weird high pitch where it sounds something like this. Hello, I just inhaled some helium. Okay. Something along the lines of that. They're usually colorless and odorless, and they're gases at room temperature, right? Literally the most famous one here is neon. If you ever go one of those like rock concerts where like everything is like black and like the lights are off and the band's going, and before you go in, they hand you these little sticks that look grayish until you go in the movie theater and go like this, and then they start lighting up. Yeah, those have neon gas in them. And breaking it like this, you're basically releasing small pockets of the stuff and triggering its glow. And one more thing about noble gases are they are incredibly stable, right? Part of the reason they were named noble gases is because nobles back in the old days do not like to change, right? So do noble gases. They do not like to change. They have a completely full valence electron shell. This means that they rarely, if ever, react with other elements, including the most reactive of elements, for example, alkali metals. They don't react to them, right? You got the noble gases, they keep to themselves, right? And yeah. And yeah, right here, I need to mention this. Noble gases are known as inert gases. Basically, what this means is that before xenon was discovered to be able to react with fluorine and oxygen, scientists thought the noble gases were completely incapable of performing chemical reactions. And that's how stable and unwilling to change these gases are, which is actually a good thing because they cause less explosions. If only solids were that way. Anyway,